It's Nakul and Tobias. They're going to present the real-time monitoring for distributed systems.
Thank you. I hope everybody had a good lunch. I'm Nakul, and together with Tobias, we're from Trademob. Trademob is a Berlin-based startup, and today we're going to be talking about how we do monitor our systems in real time. Just to give you a bit of context, Trademob is a mobile app marketing platform. We do things like user acquisition for apps, and we also do retargeting, and we're among the largest mobile demand-side platforms in the real-time bidding ecosystem. The talk will be actually split into two parts. I will give an introduction to the engineering aspect of how we do monitoring, and this will be followed by Tobias talking about the techniques and the algorithms that we use in how we do things. As a demand-side platform, you can imagine in the real-time bidding ecosystem, we are dealing with anywhere between 10,000 requests per second to 100 or 150,000 requests per second on any given day. This means that our infrastructure has to actually organically scale based on the traffic that we are receiving. Now, we believe that no matter what scale you are, it's very important to measure anything and measure everything. The metrics give us an insight and an overview into the systems, which lets us improve our mean response to detect and to also respond to these issues. Not to mention, we get an operational overview at different levels of granularity. However, at the scale that we are working at, we range from anywhere between 100 servers on a given day to 500 or plus servers. At this scale, the number of metrics, the sheer amount of data that you're collecting becomes overwhelming. You cannot expect to have dashboards and expect developers to be looking at these dashboards and come to conclusive decisions that actually help in how you are dealing with the metrics that you're collecting. Now, while we are facing this problem, there was a trending topic that came up in the ecosystem and the community. Companies like Twitter and Etsy, they've been pushing to something known as anomaly detection or outlier detection, which is quite popular in a lot of telemetry data. Now, we thought this is a good idea. We could detect anomalies in our applications and our infrastructure and actually react to these issues. But when we actually put it into production and we observed that this was actually not really useful just itself, because the number of false positives that we got with anomaly detection was fairly high. And we ended up actually doubling the number of alerts we would get from the infrastructure and the monitoring stack that we had. Now, at this point, we said, okay, this is not clearly working for us. We need something smarter, which means we would have to put in more machine learning on top of this. So we thought some other ideas, such as seasonality or convergent cross-mapping, could be a lot interesting for us. So when we combine the signals from different algorithms on top of our metric data, we could actually come to conclusive decision-making based on the signals that we are getting from this. So to sum it up, anomaly detection itself is an extension to your toolkit, and it alone cannot give you conclusive evidence to make your decision and react to events in your infrastructure. However, another problem that we had at this point was there wasn't a single piece of software or system that could actually enable us to do all of this in rather easily and abstracted this against our developers and in terms of operations as well. So we decided that we need to build something for this. But to do this, we had a set of clear requirements. Among them were this had to be near real-time, or at least near real-time. Why I say near real-time is because when you're collecting metrics data across your stack, it flows through different aggregation policies. So if you're using something that is popular in your like StatsD or Carbon, these metrics flow down to your final end of the funnel at different levels of interval. It could be 1 second or 10 seconds. So it's almost real-time, but it doesn't necessarily have to mean that it is not real-time at all. We also needed isolation. So if you're applying different algorithms on top of the same telemetry data, this means that we have to enable these algorithms to run independently and in a non-blocking way against each other so that we can decide based on the evidence that we can get from the data. Besides this, it had to have a really low footprint. So if you're trying to optimize your infrastructure and your performance based on the number of instances you're running, you cannot expect to have a system that actually takes up a lot of resources. This metrics or monitoring system has to have a really low footprint so that you can actually optimize on your costs. And it had to be extensible. What I mean about extensibility here is in terms of the algorithms itself. It had to be really easy for us to plug in new algorithms and new ways of looking at the data, and also the data sources themselves had to be really extensible with interfaces. So we went about building a system called Anomaly. Anomaly is basically a system to gather metrics selectively and then apply analysis on them. And this is all abstracted from the developers into operations so that it's fairly easier to set it up. Now, this has been used at Trademob extensively to actually optimize our cost at an infrastructure level by monitoring the performance. And it has also helped in bringing down the number of alerts that we would normally get. But before we could actually put into production, we had to do something that was very important. We had to scope the metrics. Now, when you're talking about metrics, there are basically two levels of metrics that you normally collect. One is application metrics themselves, which come down from your services, like how many requests am I doing in a given second, what is the latency for each request, and so on. And the second would be your system level metrics. What does my CPU look like? What is the amount of memory that I'm consuming, and so on. Now, by scoping, what I mean is we needed to look at this metrics at different levels of granularity. We wanted to know how much CPU we were consuming as a whole service itself, but also at different levels of clusters. Say if you are dealing with autoscaling groups, we wanted to know how much CPU is this autoscaling group consuming as a unit. How much of memory are we consuming globally in a given region? Now, when we take these different levels of granularity, we can then use this data to come to better decision making. I can give you a simple example on this. A simple metric that we have basically looks somewhat like this. You have host, you have the region that it is coming from, the availability zone if it applies, the autoscaling group, and the particular tag of the service itself. Basically, each one of these is a tag that is separated by a colon. Now, when we actually multiplex, this would actually yield a number of combinations that actually make sense. We get metrics at different levels of granularity. This would then have to be passed into different levels of aggregation so that you can get more evidence and compare this data to actually at different possible levels. To actually summarize, this is what our tech stack looks like when we collect the metrics and monitor them. We have a bunch of services at the top that are all sending the data to a multiplexer or an aggregator, where the data is then multiplexed, aggregated at different interval levels of period, and then it is pushed to a layer called collector daemon. Now, the collector daemon is a libuv-based Python implementation that is basically a server that just lets you selectively collect data that your operations team or your developers are interested in, and this is further then pushed down to a metric store layer. The metric store could be any generic key value storage or a database, depending on what you're using in your technical stack. Now, once the algorithms are actually pushed into the system, there's a task runner that is capable of periodically running these algorithms against the data from the metric store, and it then triggers events. These events are then fed into an external system which is capable of triggering actions. These actions could be such as, if the algorithm determines that one instance or one server of yours is not performing optimally, then you can decide to kill this instance. Since you're in an infrastructure level, you're performing at an autoscaling group, which means that, okay, you can choose to kill this instance, or you can choose to restart a service, or so on. So what Anomaly actually provides us is more of a framework that lets us push the data into the system and have different algorithms look at it in different perspectives. Now, Tobias will give you more insight into the math and the science behind the algorithms themselves that we use to do this.
Yeah, thanks, Nakul. I'm going to present the algorithmic part of Anomaly, and first of all, I would like to start with a short introduction how anomalies could look like and what possible ways there are to react on them. So the first example is rather simple. It just shows the CPU utilization of a single box, which suddenly peaks at 100%. And of course, you can catch this by just applying a static threshold. And if this gets exceeded, you can react on it. The second example also shows CPU utilization. In this case, it looks rather stable at the first glance. It doesn't look so if you put this into a context. This means the green, it's supposed to be green area, defines something like an expected state of the box. And yeah, obviously the given box is not into this area. So you could also say after a certain period of time that this is misbehaving in some way. And the third example is a time series plot of incoming system metrics. And we see 3 consecutive days in here. And I guess it's also obvious that we had some issues. The question here is, what kind of algorithm is applicable to find those outages? And yeah, if we wrap this up, it all comes down to the point that before you can do proper anomaly detection, you need a way of defining what you expect from your system or from your service. And only then you can really define some situations as okay or as falsy in the end. And in the following, I would like to go into 2 directions. The first one is the behavior of the distributed system. So as Nakul mentioned, we have a couple of distributed services, which sometimes contains up to hundreds of boxes. And now the question is, how do single boxes behave within such a group? And one way of doing this is so-called Taki's outlier filter. So what we see here is a snapshot of CPU values. So it goes from 0 to 100, and each blue dot is just representing one box with the CPU value at this time. And what we see, it's quite dense between around 50 and 60%, but there are also some boxes which are much below that or much above it. And one way of judging this is using quantiles. So what we see here is the quantile 25, so just the cutoff between the lower 25% to this upper 75% of the values of this distribution, and accordingly the quantile 75. And if you take the difference of those 2 values, you get the so-called interquartile range, which just gives you kind of a robust statistics for the middle 50% of values. And if you now multiply this value by a constant and add it up to the quantile 75 or subtract it from the quantile 25, you get this green band. And in this case, we would define this as a healthy state or as an expected behavior of this service group. And every box which is not within that would then be defined as an outlier. Of course, this is only a snapshot. We are handling time series data. So in practice, it looks more like this. So we have a couple of metrics plotted here, and we have again this green band, which is exactly the same like on the left plot. And there's one box which is running only at around 10% of CPU. So basically, we are losing money at this point of time because it's not consuming what it could use. And you can now set thresholds, like if this happens for more than 1 hour, 2 hours, whatever, then you can react on it, like restart the service on the box or even kill the box and just boot up another one. Quick summary of this. So the idea is that we want to identify auto-scaling issues. It's not only about CPU usage, it's also about memory leaks, or you can also think about business KPIs like requests of a single box compared to the others. The restriction here is, of course, that you always need a healthy range. So if all your boxes do misbehave, you would still define this interquartile range and would still define a healthy range, even though your whole service has problems at this moment. And that leads us to the second part, which is the performance of the overall system. So one last word to CPU. If we think about a service consisting of a couple of machines, you can judge this also by just taking the average CPU utilization. And if this metric has issues, of course, you have a much bigger problem than just a single box, which is misbehaving in this case. And well, there are a couple of algorithms how to tackle this. What we are currently using is so-called seasonal trend decomposition algorithm. We see here a time series plot of 7 consecutive days, and I guess it's quite obvious that there is a given seasonality. So most of our metrics have this seasonality of 1 day. So we see more or less the same pattern day by day. And the algorithm is exactly using this. So it's taking this as an input and it's generating 2 components of this time series, namely the seasonal part and the trend part. So seasonal, we see it's more or less identical over the 7 days. And the trend component is able to catch things like if you have a constant increase of traffic, for instance, so it would be reflected in here. What we see in this example, that it's rather stable in the beginning, and it has a slight increase during the end of the metric, and that is for a good reason, because if you look at the days, you can find the weekend in there. So Saturday, Sunday usually have more traffic, and this, in this case, gets just reflected by the trend component. How do we do that, or how do we use it to find anomalies? Another example for that. So we see 2 days here for incoming traffic. And okay, we also see the outages already here. But one way of doing it is now to apply the algorithm to create seasonal and trend part. And you can now just add them up. So if you add the 2 time series up, you get kind of a model of your service. So this is exactly what we would expect from this service by just using historic data. So of course, we are not looking at only 2 days. We look back up to 14 or even 28 days to reconstruct this. And with this model, you can just combine it with the raw input and take the difference. And of course, then it's quite obvious. So we have the deviation distribution now, and with the proper threshold, it's quite easy to catch those through outages. Unfortunately, it doesn't look that nice all the time. So error distributions look more like this, or even worse. So we have peaks, we have drops, and the question, of course, is when do you want to react? So what is this threshold or state where you would say, okay, there probably is an issue, and of course, you always want to have a very low number of false positive, but you also don't want to miss really problems. And that is a big part of the whole problem. So the algorithm is producing this error distribution, but to really get the information out of it is not that easy, and often quite specific for specific metrics also. I just put in here some ways how you can act on it. One is normalization. Others are minimum deviations before you want to even start alerting or reacting on it. There are static thresholds, which are a bit complicated because you need to know beforehand what kind of deviation you would allow or expect. And the way we are usually going are dynamic thresholds, where you can just set up something like a 99.9 quantile, and if values are above this, you react on it. And if you apply this, or combinations of this, then the output looks like this. So we have just a flag now, which indicates if everything is fine or if we are in an error state. And depending on the length of such an error state, we can take actions like restarting services, or of course, alerting people, because in overall performance metrics, there usually are bigger issues who or have to be investigated further. And for now, that's all about Anomaly itself. The last part is going to be about dynamic thresholds. So how do we estimate those ones? And what we use for this is a data structure called T-digest. It's originally implemented and I guess invented by Ted Dunning. And the problem is that if you have a lot of real numbers, and that's exactly what those error distributions reflect, then of course you can do the lossless approach. You can store all those values, you can order them and calculate the quantiles, but you can do smarter. And that's exactly what T-digest is about. It's basically an online clustering of real number values, and it has the purpose to create rank-based statistics such as quantiles. And by doing this, it's quite fast and memory efficient. And what's very important for us is that it has a very high accuracy for especially extreme quantiles. So in the very low end and high end, and that's usually things where we are looking at, of course. I would now like to go through a bit the algorithm, just to give a rough idea how this is working. The key concept or the key element of a t-digest is a so-called centroid. So a centroid has a mean value. We will see that on the x-axis afterwards. It has a capacity, which is, its capacity, and it has a count, which basically reflects the number of elements we already added to this centroid. And the example now is just a stream of 10 real values, and yeah, we want to add them now. One more words to the centroids. So the idea is that you keep an ordered list of such centroids, and always when you want to add a new value, you search for the closest centroid, and if this centroid has enough capacity, you add the value to it, otherwise you create a new centroid. And yeah, let's just go through the numbers. Of course, in the beginning, there is no centroid yet, so we just create one. Yeah, sorry? Yeah, we'll come to that in a second. Yeah. So the first centroid is the mean value minus 3.58. And it has a count of 1 because it's just one element. And in the beginning, it also has a capacity of 1. So that's just our first centroid. And if we now move on and add the second element, which is 3.77, again, the algorithm tries to find the closest centroid, which is the only one which exists right now, but the capacity is at 1. So we cannot add a new element with a count of 1. That's why we have to create a new centroid object here, which looks like that. And the same happens for the third number, so minus 15.26. If we add it, we try to find the closest one, which is here the left one, but it still has a limited capacity, so it's not able to get a new value. So we create a third centroid, and now something interesting happens, and that's mainly the idea behind t-digest. So the capacity of the centroids change over time, so they get constantly re-evaluated after inserting a new element. And yeah, we are now in the situation that we can add a new element, which is minus 1.82. We find the closest centroid, which is exactly this middle centroid, and this one has now a capacity bigger than 2, so it has enough room to add one new element, and this is exactly what happens now. So okay, I go, sorry. Right, so this is the closest element, and if we add this, this happens. So we see two things. One is that the small blue dot, sorry. So here, we see the count increases to 2, and also the mean shifts. So we have a slight shift to the value minus 1.82. And yeah, that's the idea, and that is how you build up a structure like t-digest. I don't want to go through all the details or all the numbers now, but yeah, if you add all the numbers, for 10 numbers at least, you end up with something like this. What we can also see here is that we have 10 real numbers, but we also only have 8 centroids. So we also have kind of a reduced number of elements, and this scales quite well over time. And the next slide is coming back to your question also. Of course, the question now is how is this capacity thingy working? And the idea of a centroid is the following. So it has a capacity which is proportional to a factor delta, which is namely a free parameter which you can set. And you do not set exactly the number of elements you want to add, but this is like a trade-off between storage you need and accuracy in the end. So you cannot preset it, but if you choose it very, very small, you have a lot of centroids, but a very high accuracy. But yeah, so usual values are somewhere around 0.01 or something like that, where you already have a quite high accuracy. And the second part of this capacity is the value of the quantile times 1 minus the value of this quantile. If you plot this, it looks exactly like this, and this is the magic behind it. So what we see is that the capacity on very small values, so around 0 and around 1, is very small. This means if we add a new element in this range, also a quantile in this range, then the capacity is quite limited. This means we often have to add a new centroid, which makes higher accuracy. But if we are around the median area, capacity is quite high, and there we can put a lot of elements into one centroid, and that is where you store in the end, or you save the storage. And yeah, to wrap this up, we have low capacity on extreme quantiles, and therefore high accuracy at extreme quantiles, and that's exactly what we are looking for. And yeah, with that, I would like to finish with the algorithms. Last but not least, I would like to announce that we decided to open source both projects. So we will do that in the beginning of June. So one is the whole Anomaly project, including the algorithms and so on, and the other one will be a Python implementation of tdigest. And yeah, feel free to download, to use it, to contribute. We are looking forward to that. Thank you very much.
Questions?
I think the ecosystem, especially when it comes to monitoring, it's very fragmented, and there are a lot of tools. And we had to reinvent the wheel when we did this. So we think it'll be appreciated by a lot of others as well. Because if you're operating at scale, and I would imagine that you would want to do something like this. So I think overall we feel that it'll be useful to the community, and we want people to contribute more algorithms at the end of the day so we can improve our system as well. We do use StatsD and Graphite as well, but this is the very lower end of the funnel. So our metrics flows through Graphite, multiple layers of carbon, and one of the endpoints is Graphite and another is Anomaly. Graphite is just where you would plot graphs and see as a developer, and Anomaly is where you would have a hands-off approach as as an end user and expect the system to actually detect issues. No, absolutely not. Whisper doesn't necessarily scale. We do use Whisper as a backend to Graphite, but the metric store that you saw in the overview, for us, it's Redis in this case. And I think going by your talk in the morning, we would like to explore BLOSK, if I'm right, for time series data because it makes sense. Sure.
Yeah. Yeah. You can merge them, yeah, right, it's possible. Not yet. So it's at the moment it's still kind of a basic implementation. So there's a reference implementation by Ted Dunning in Java. But yeah, we'll work on that. Also adding different tdigest objects. Yeah. Yeah, sure. Okay.
All right, so let's thank again Tobias and Nakul.